among the many different distribution shapes out there, then when the probability distribution of a continuous random variable x has a symmetric bell shape. So here's a PDC, and when that PDC create a probability distribution shape that's looking like a bell shape like this, like a bell, then the probability distribution here is called a normal distribution. And so on this bell curve here, this horizontal line represents all values of our random variable, our continuous random variable x right here. And so just as usual, the values of x go from low to high, from the left to the right. A different way of saying is that we can say the continuous random variable is normally distributed. And then when anytime our continuous random variable is normally distributed, then as I said earlier in earlier video, then for a continuous random variable, for any continuous random variable, mean value would need to be calculated and given to us. So mean is given, and also standard deviation, population standard deviation is given. And so the specialty about the normal distribution is that mean value, and it makes sense that since the bell curve here is in that has that nice one peak symmetric right in the middle, and so the mean value is exactly in the middle. And this is also, as a reminder, this is also where mode, because high peak happens there, and median also meet at the same value as well. But when we're on the normal distribution, mainly anytime we're looking at the center, then we refer to the mean value. Standard deviation, population standard deviation is not always trivially seen in the picture, but we can always note the value of the standard deviation somewhere near the bell curve picture. And of course that represents the random variable x. So those values of the x stays to the left hand side of the mean, represent those values being below mean, and of course those to the right hand side represent values that stays above mean or above the center. And in the end, a normal distribution is a probability distribution, and we've learned from previous video lessons that anytime we're looking at probability distribution formed by a PDC like this, and remind yourself the curve itself here is a PDC, and so anytime we're looking at a PDC or a probability distribution formed by a PDC, then the total shaded area inside a PDC cumulatively is always 100%. And so that is no exception for the normal distribution. So in other words, the total accumulated area inside a bell curve right here is always 100%. That represents where all data is. So this is where all data is found. And that's why it's 100%. So all data is found inside this curve. Or it's, once again, it's the accumulated amount of area being totally 100%. Now, another thing to notice about this bell curve here doesn't really end. It's the two tails keep getting smaller, but it's going to extend infinitely. We are in the end only in an introductory class of statistics, so we don't have to get too far details about the asymptotic nature of that or anything of those fancy terms. But in the end, keep in mind that our normal distribution curve will not end on the two tails right here. It's going to actually keep extending infinitely to the horizontal line right here. And so at this point, I have to make clear one thing. So at least in this class that we are learning, being an introductory level of statistics, then we will never have to verify how our data forms into a normal distribution. So in other words, this piece of information telling us that the random variable x is normally distributed is always given, and that's why I'm putting a red check here. And as we discussed in previous video lessons, then when we're looking at continuous random variable for our level of learning statistics here, then we can only take a given population mean value, and we also have to take a given population standard deviation value. So in other words, any other time that any time we're about to work with a normal distribution, we already told that our continuous random variable is normally distributed with a given mean specifically given and with a given population standard deviation. And so now let's say, now you know that you're working on a bell curve, you're working with a bell curve with the data that's on a bell curve. And we know that we have a mean right in the middle, a given mean, and our random variable is being on a bell curve once again. And we have a standard deviation given, population standard deviation given. And so normally or usually the worded statements to describe our data being given as a normal distribution, here's the standard way of how the data is being worded. The problem is being worded: x is normally distributed. And x could represent a lot of different kind of data out there, but formally we're saying that x is normally distributed. So that one piece of statement right here is indicating for us that now we have a bell curve given. We have a data that's on a bell curve. It's given information. And then furthermore, the statement continues saying with mean at mu right here and standard deviation sigma. So this is formally a worded description as a way given to us that our data that we're working with already been known to be a normal distribution and having a mean value at whichever calculated mu value and the standard deviation sigma. But now saying out is simple, but a lot of time when we write it down right here, it takes a lot of time to write, and so we come up conveniently with a symbolic statement. So all that worded statements to describe our data can be now represented as one symbolic statement. So x is the random variable and is distributed. So this symbol over here, this wiggling line right here, is to indicate is. So here's how it reads: our random variable x is distributed. Normal distribution, we use a symbol capital N letter with a pair of parentheses. So this N here is indicating that we're having a bell-shaped distribution. And inside of that pair of parentheses, we're putting the mean, the calculated mean value, and the standard deviation value. So surprisingly, this one simple symbolic statement right here represent all that worded statements. So think about the effectiveness when, instead of writing the worded statement like this, we can just quickly communicate in written form as a symbolic form like this, that x being distributed by a normal distribution. Or a lot of time I also say that this is x, the random variable follows a normal distribution. Many different ways how you can understand, but this is one legitimate symbolic statement for quick and effective way to describe a normal distribution that being given to us. So to really demonstrate my idea, that idea about using a symbolic statement is to represent, to describe we having a normal distribution data to work with. Then let's look at this quick example over here. So this example here is not really a problem yet, it's only a description of the data. So let's have a minute reading that. So SAT scores. So we can see that dangerously there is a plural right here indicating that we have a lot, but simply we just don't know how many scores there are for that year. And so SAT scores, so that brings up the understanding that here we are looking at we're working with a population data. And so SAT scores in the year of 1997 were normally distributed. So now here I start giving that piece of information right here. So the worded description is telling us that our data being SAT scores, the distribution there is a normal distribution. So start thinking about that bell-shaped curve right there. And would mean calculated being 950 and standard deviations being 150 right here. So once again, as to emphasize what I explained previously, then these three pieces of information always come along anytime we are about to work with a problem on the normal distribution bell curve. But so this worded statement, think about if we assign a random variable or if we define a random variable to represent. So how about capital X to represent an SAT score? So once we define that random variable X to represent an SAT score here, then the way it says now wordedly, it says X is a random variable that's normally distributed with mean, etc., etc. But surprisingly, all that can be written symbolically as one convenient form here. X being distributed by a normal distribution, by a bell curve shape with center with mean at 950 and standard deviation 150. This one symbolic statement takes half a second to write it down, but surprisingly represent the entire worded description of our problem here. SAT scores, we're given that definition of our random variable and being normally distributed with mean given here and standard deviation given. And informally but widely used out there, people even for short refer to a random variable X that's normally distributed with mean at 950 and standard deviation 150. Even a shorter way of saying that, for short, we just say all that information here is an N 950 and 150, because one little symbolic expression here represents three pieces of information. We have a normal distribution, meaning it comes into our mind the picture of a bell curve, and the mean is at 950, which is right in the center, 950. And the standard deviation here is also calculated and given to be 150. And as I said earlier, not too clearly seen in the picture, but we can always note it somewhere for later calculation purpose. And so from this point on, right now, a lot of time when you hear people among the statisticians, when they communicating, they're saying it's an N 10 2.5, for example. Okay, this really means we have a random variable, or some random variable X maybe, that's normally distributed with a mean at 10 and standard deviation 2.5. Or an N 1 comma 0.05. It means so this is a short symbol, but it means some variable, maybe x or y or t, whatever, is being normally distributed by a bell curve with center at 1, standard deviation 0.05. And so now, once we're on a normal distribution, or once we know that our data is on a bell curve, with mean generally at mu and standard deviation generally at sigma value, or symbolically x normally distributed by an n mu sigma, once again the picture that comes through our mind here, the imagination that comes in our mind is all the data here after histograms turn into a nice bell curve PDC like this, and of course mean value mu is now right in the middle, and we just simply make note of some standard deviation sigma value on the curve somewhere. And once again, left and right on this horizontal line is the place where all different values of our random variable x being arranged there. And once again, briefly review that left hand side of the mean here is where those values being below mean, and the right hand side of the mu value here is indicating those values of x being above mean. So now, once you know that you're on a bell curve, then again, in the end, a bell curve is, as I said earlier, is simply one among the many other continuous random variables. So x here, the random variable on this bell curve here, is a continuous random variable. And so the reason I mention this is because once we know that x must be a continuous random variable to be on a normal distribution, then in the end the random variable x here must have all those properties for being a continuous random variable. Meaning, as I said earlier in my other video lessons, then when we're on a continuous random variable, then and even with a given PDC, at our statistics course level here, we won't be able to find out how much probability when our random variable precisely equals a value. So let's say it could be a value a here to the right or to the left hand side of our mean value on this bell curve, but I'm not saying that we won't have an answer here. I'm not saying that there is not a way, but not at our level of the statistics course that we're learning. So in some future course, a lot more advanced than this. But so now this question here, just like how I explained about the general continuous random variable, then this question must be ignored. We can't find an answer for this question here at our level. But since this kind of question is being ignored in our level of the statistics learning, then we're actually going to turn our focus into answering different kind of question. And just like, again, like I said back in my video lesson for a general continuous random variable. So here on a normal distribution, we can't answer the question probability when x precisely equals a value. But instead we can answer the question where the probability that our random variable x takes value inside an interval from a to b. And so this statement of mine is saying that I'm looking for, so maybe on this picture here, maybe a is a value somewhere on this horizontal line, and b is another value to the right hand side. But now I'm looking for, as the way how my inequality here is reading, then it's saying x is greater than or equals a, less than or equals b. So that means here we're producing for ourselves an interval of value. And so this probability question is actually, so this question can be answered. So we can answer this question at throughout our course here. And so, and once again, connecting with the lesson we've learned for general continuous random variable, the probability when our random variable takes place inside an interval like this is represented graphically graphically represented by a shaded area between A and B inside of that PDC. And so that's what I just need to emphasize about what we mainly learn as far as anytime we're working on a bell curve here throughout our course. And now before we move on too far over here, if anyone is looking at this picture here and then looking at seems like we have a curve, and then inside the curve we're having an area shaded inside the curve and between two values, and then this question about finding the probability when our variable takes values between or inside an interval like this, then it's produced a shaded area. So really we are calculating how big that shaded area is. Then I have a note for anyone who happens to have so much calculus understanding. But a problem like this, yes, it does bring up, for those who have a lot of calculus background, then a problem like this really brings up that connection with doing an integral work. But I have to emphasize here, our class here, we don't need to bring in any calculus at all. So there are no calculus required here for this kind of problem, just to make clear. So anyone can really do this work right here. We have other way to handle the area here, and I'm talking about exact value, but no calculus required here. I mean, if we have to use calculus, then you actually need to wait for another advanced course where you actually know what functions generate a curve like this in order to be able to use the calculus and the integral work right here. But here at our level, once again, as I said, we are at the very introductory level of statistics, so we don't need to bring in that tool about taking integration and all that, so no calculus required. We're gonna be learning a different tool to handle these areas between values inside a PDC curve. And so to continue illustrating that idea about for our level learning statistics right here, when we're on a bell curve here, instead of answering the question, find a probability where x equals precisely a value, we must ignore that. But instead we're turning our focus into investigating those questions where we find a probability that our random variable takes value inside an interval. Let me quickly demonstrate, and of course we haven't gotten too far yet within this video lesson, but at least I can point out there's one example that exists within our capability right here. So let me bring up a quick example to point out that this kind of problem really exists a lot throughout our work. So how about we are given, or we can just be looking at any general. So giving an n mu sigma. So now that brings up, we have a normal distribution, a bell curve shape. And I highly recommend that anytime we're working with a bell curve shape, even if you don't have technology, try to get for yourself a hand sketch bell curve like this and start making the shading as described in a problem. It's going to help a lot in terms of having the problem solved successfully. But so once we know that we are given a bell curve here for whatever random variable name, we can just call it random variable x. Mean has to be strictly in the middle, and with some standard deviation, we don't have to see how much it scales in the bell curve, but we gonna note it somewhere. But let me bring up this quick question here in my current example. We can find, so on this normal distribution at center mu and standard deviation sigma, we can find, and read my question along as I'm writing it down right here, but p in parentheses, how about x less than or equals mu? So how do I see an interval in this problem right here? It truly is an interval. So on my bell curve, mu is here, right in the middle. And then this question, we've learned that since our time learning probability, but this statement says we want to find a probability where our random variable, in the event that our random variable takes value less than or equals mu. But less than or equals mu here, this probability question is actually is actually having a graphical representation. It is the shaded area, but completely to the left-hand side of where our mean is. And once again, remind yourself that our mean is exactly in the middle. And so, with a problem like this, surprisingly, we haven't learned any fancy tools yet, but we actually know a way how to handle this. First of all, I remind everybody that in the end, a bell curve or whatever curve being a PDC, we strictly must nail down that the total accumulated area inside a PDC is 100%. So there's always 100% here of data being inside of our bell curve, or being inside of our generally PDC. And now our PDC here is particularly being a normal distribution. And so in that case, center is here, and we're looking for the area only to the left-hand side of our mean right here. And knowing another fact, that mean is exactly right in the middle. And our bell curve is being now ideally a perfectly symmetric bell curve. And so that means the entire area here being 100%. Now we can just simply cut it in half, because we're only looking for the area one side of it. So I'm doing a little bit brutal description here, but I have to erase one area to the right-hand side, because we're not looking for that. We're looking on the left-hand side of mu. And so now this answer is taking full use of making use of our understanding, taking advantage of the symmetric nature on the bell curve. This answer here is simply the probability where a random variable takes value anywhere less than or equals mu on any bell curve is simply a 50%. And remind yourself, mean value on the bell curve is also where median meets, and mode is also here at that same spot. So it makes sense that 50% of data falls below the median again. And so, but now the only thing we switch to is, instead of using percentage convention, we're going to write our final answer as a decimal. So 0.5 is the answer. 50% is also work, but a lot of time 0.5 is the more welcome kind of answer format right there. And so, very similarly, given again that you're on an n mu sigma, or be on a normal distribution with mean at mu and standard deviation sigma, then once again, before we even try to answer any questions, go ahead and have for yourself a hand sketch version. It doesn't have to be a nice looking one. But so mu is here in the middle, sigma is somewhere being noted there. But this time, how about I'm going to bring up the question, find the probability where our random variable is anywhere greater than or equals to the mean value. And so, once again, what we have here in this inequality description is an interval to the right-hand side of our mean value. And so that finding that probability where our random variable takes values greater inside of that interval, it means it's graphically represented by a shaded area inside a PDC, inside our PDC being a bell curve. And so now the way we are reasoning this problem is exactly like the way how we reasoning the earlier quick little example. Here there's always permanently 100% of data completely shaded inside this curve. And so the area we're looking at here is only to one side. So needless to argue too far, this answer has to be 50%. We're taking full advantage of the fact that our bell curve here is, well, precisely the symmetric. So each side way here is only half of the complete 100%, or in decimal, 0.5.